Hello. So we are going to find the amount of chocolate on a cookie that is shaped like the region between y equals x squared and y equals 2 minus x squared, where x and y are in inches, and our density function is given as 4 minus x squared minus y squared grams per square inch. So the first thing I'm going to do is I'm going to draw a picture and then imagine chopping up the inputs like we've been doing on the examples so far. So the picture, I have y equals x squared, which hopefully I know looks like this. And then I also have y equals 2 minus x squared, which is an upside down parabola that crosses at 2. And then my cookie is that region in the middle. Right. So when I chop up the inputs, I'm still going to chop up my x's, and I'm going to chop up my y's, and I imagine all these little squares of area delta x delta y square inch, or delta y delta x square inch. And to calculate the amount of chocolate on a small piece, it's just what we've done so far, sigma dA grams, right? Sigma grams per square inch, and then dA square inches, where dA is dx dy or dy dx. And then where it gets interesting is for me to add this up over my cookie to get the total amount of chocolate. So I'm thinking of either adding up 4 minus x squared minus y squared dx dy grams of chocolate, or 4 minus x squared minus y squared dy dx grams of chocolate. And it's important to remember what this is doing on my cookie, like the shape and the picture. So if I do dx dy, I am fixing my y and then adding up along the x's first. If I do dy dx, I'm fixing my x and adding up the y's first. So with one, I'm adding up along a row first. With the other, I'm adding up along a column first. And one of these is easier than the other. Notice that for the dy dx, where my y starts and where it ends is on a bottom curve and an upper curve. But for dx dy, where my x starts and where it ends depends on which y value I'm at. If I'm above this horizontal line, y value, then I'm between my top curves, two sides of it. And if I'm below that horizontal line, I'm between my bottom curve, two sides of it. So that one's going to be a little more complicated. We'll do that one second. And we'll do this one first so we can see how the limits of integration work in this setting. So just because of time in class, I wasn't able to write all this out last time, but what I should do when I'm setting up my limits of integration, I should ask myself in my head, for a fixed x value, what do my y values vary between? And notice this can depend on the x value. And in fact, in this case, it does. So I start at my bottom curve and I go to my top curve. So I start at y equals x squared and I go to y equals 2 minus x squared. So the answer is my y values go from y equals x squared to y equals 2 minus x squared. And that gives me my inner limits of my integral. And then for the next question, I ask myself, for what x values do I add these columns up for? And again, back to my picture, I think about all my columns, and I just need to figure out what x value I start at and what x value I end at. Well, that's coming from where y equals x squared and y equals 2 minus x squared intersect. So I'll look for their intersection. X squared equals 2 minus x squared. So 2x squared equals 2. So x squared equals 1, or x is plus or minus 1. So I do this from x equals negative 1 up to x equals positive 1. So my integral winds up being the integral from negative 1 to 1 and the integral from x squared to 2 minus x squared of 4 minus x squared minus y squared dy dx. And that's my total grams of chocolate.